Okay, let's get started. Okay. Let's get started. Ready to start? Here we go. Ready to start? So, lots of you, some of you, are ready to start? Okay. So, some of you have stopped by, and I see you have started your work on this. That's great. Any questions about this project? So, one thing I'll say to start is this idea that showing all 10 of the steps all the time to make it easier, it doesn't make it easier. So I just made a really, I just basically took that function and then just only graphed it from 0 to 3. So it's, the program is creating all 10 steps, but then you can just very easily just show it from 0 to 3. Okay, and so that's a little bit better. Now I have to do, I think the same is true, but I'd have to go in and change. I'd have to change all. Same thing is true for the accumulation part. I'd have to change all 10 of them. Okay, so I'd have to change all 10. I just didn't take the time to do that. Same thing, so that it would only show from 0 to 3, and so that would mean no matter, just a simple adjustment on all 10 of those lines graphing those segments. Okay, so now I'm going to give you a chance to ask some of those who dug into it and have questions.
I don't understand what you just said the difference is between now and before.
So before, for this graph, I was just always graphing all 10 steps, even though that went beyond our the range we're interested in, 0 to 3. So now it truly only shows the steps that are in that range from 0 to 3, no matter how many I'm showing.
Is it okay to still graph all of them, or do you have to stop at 3?
It's very, very easy. It will take you less than a minute to add something to make it stop at 3. So do that. Yeah.
Is it in the same command line?
It is in the same command line, right? Because that's just one command. It's one command line that graphs those blue steps, and in the same command line. So maybe there's an order issue. There's many things in that line so maybe the order is important. If you're having trouble with that part of it, just let me know and I'll help you. Okay? Yeah. But the most important thing is that you can graph these steps in one line that are the correct width for the values of n, for different values of n. Okay? That's by far the most important. But it's nice if it just shows it from 0 to 3. That's just a little icing on the cake. Yeah. Morgan.
So I know you said that you couldn't do it for the, or you just didn't do it yet for the other one.
Right.
Do you want us to do it for the other?
Yeah. So if there's anything that's easy that makes it better, do it.
So like
Yeah.
if we do choose to make this one only shown from 0
Uh-huh.
to 3, that's okay.
That's better.
Okay, that's
It's better. Yeah, it's better. Mhm. I just didn't take the time to do that. Yeah. I think I just before class I just changed that one. Didn't have the time because it'll take longer because there's all those different. Yeah. But yeah, that's better to show it from 0 to 3. Okay. Other questions? So there are people, they're making progress, having success on this. In terms of working together, I encourage it, and just as long as it's appropriate. The way that you're doing it is appropriate, and so that means work together, figure things out together, and then go off and write it yourself. Okay, that's the key, right? Work together, figure things out together. That's great. Dialogue, put your heads together to figure things out, and then everyone go and write your own. So then, when I'm grading, some things pop out at me, things that look very similar from one person's to another, and so then I put the S after your grade, which means I noticed that it looked really similar to someone else's. So what does that mean? It's only a problem if that becomes a pattern. So if you have one S or one S and then one S like later, this isn't an issue. But if it's a repeated problem that's over and over and over again, I see 4, 5, 6 S's on your assignments, this is where it becomes an issue, okay? So it's just whenever you get one, it's just a gentle warning. Just a gentle warning. Make sure you're doing your own work. And so I realize that some of that may be coincidence too. That's why I'm not penalizing you for it. Okay? If you get an S, you don't get penalized, because I realize that occasionally there would be a coincidence where it would look just the same and you didn't even work with that person. Okay? So, but if there's lots of them, then becomes a problem. Yeah.
Is that like X is greater than 0 and less 3 or 30?
30. Yeah. So the actual rate function you could just show. It doesn't matter how much you show. You got to show at least 3, but you can show more than 3. And that's no problem. That's the actual rate function, right? The curve. How much of it do you want me to show?
I don't know. I just saw last time you showed the
It's yeah.
So this time
That's very doesn't matter as long you got to show at least 3. Sometime I was messing with my file and I wanted to make sure I showed enough. Oh, right. I wanted to make sure I showed enough when n was small and those steps were big, and so I wanted to see it up to 30. Right? Yeah, because if n equals 1, then those steps would go all the way to 30. But that doesn't matter anymore. That doesn't matter. Just as long as you're showing at least 3 or more. Okay, other questions?
Wait, one more.
Yeah, please.
For the piecewise,
Yeah.
Is it going to be the same method to only make the lines go from 0 to 3 as the?
Yeah, it should work. Yep. When you're graphing each of those pieces, make sure that nothing gets graphed outside of 0 to 3. That's pretty straightforward. Okay. How's the tunes, Peter?
Pretty good.
They're pretty good. What's on the playlist?
Blue.
Maybe later. How about later? Thanks. All right. Should we press on? Okay. So. And I may add another task. It won't be like a whole other file like this due Tuesday, but maybe some other written task or something else for the weekend. So just be aware of that. Depending on how far we get today. Okay, so we are on this pursuit. Our pursuit is to figure out what's the big deal about constant rate of change and average rate of change. What have we been focusing on recently? Constant rate of change, average rate of change, or both? Constant rate of change. So we're starting to maybe get some answers to this question. So maybe you have your ideas. So keep mulling on this. What's the big deal about constant rate of change? Why are we putting so much emphasis on its importance? Okay, and so we're starting to see. We should be starting to see why that is. Okay, so here is a basketball. It's rocket powered. Okay, and this is the velocity graph for the velocity function for that rocket powered basketball being launched to, where's it going? It's going to Pluto to maybe regain its planet status, right? Okay, so basketballs have, I don't know, they have some kind of power over that, I don't know. All right, so quick questions here. So just discuss quickly, what kind of function is v? What do you think of that as rate of change or accumulation? So it's velocity meters per second. And what are the dependent and independent quantities? So rather than do breakouts every single question, maybe we'll just throw that out. I think these are straightforward questions. So let's see who's that. Ryan? What do you think that's a rate of change or accumulation?
Rate of change.
Rate of change. Agree with that? Right. Meters per second. Okay. And so then for this function, what is the dependent, independent quantity? What is dependent? What's independent? Oscar.
Time is independent.
He wants time to be independent. Time since launch. And what's dependent?
The velocity.
Velocity is dependent. Agree with that? Okay. Right. Okay. V is rate of change. Velocity of the rocket is dependent. Time since launch is independent. Okay, so we want to develop an accumulation function associated with V. Okay, and so what accumulation of what? Accumulation of what? So what are the independent and dependent quantities of an accumulation function? Jose?
Distance traveled and time.
Okay, so which one would be independent?
Time would be independent and distance traveled would be dependent.
Okay, what do we think? Time and distance traveled, and what's another way to say distance traveled from the ground? So height, yeah. So distance traveled, which in this particular case is height. Okay, height is dependent, time independent. Okay, very good. All right, so let's break out for these three just quickly. Question 3 is the one that has posed a challenge, but just remember what we've talked about and learned. Go, talk at your tables, these 3 questions. Okay. Okay, there's a lull in the conversation. Okay, Joey, how about the coordinates of the graph on the point of the graph at t equals 5?
We chose 5, comma v of 5.
5 and v of 5. Like it? Good job. Okay, and what does the value of v of 5 represent? How about Megan? What is that? V of 5
Use
is?
that at 5 seconds, at 5 seconds, it represents the velocity at 5 seconds.
It represents the velocity at 5 seconds. Okay, and we could also call that rate of change, right? Rate of change of the rocket's height is velocity. Okay, and so what does v of 5 mean? So what does that v of 5 is some number? What does that number mean? Jessica, you want to try? What does that number mean?
So since v of 5 gives you the rate of change
Uh-huh.
in the rocket's height,
Right.
then you can use it for a really small moment of time,
Okay.
around 5 seconds. You can use that to estimate approximate the height over the little second.
The height?
The accumulation, so yes, the height.
So, yeah, so how do we want to really specify that? Not height, but change in height, right? So, yeah, you said the accumulated height, right? So the little change in height. So it means that, so somebody else, in your own words, what does that value mean? So thinking back to the beginning of the course, and before this course, lots of you knew it on day 1. You knew it. We talked about this on day 1, and you already knew it. Any other volunteers? Jacob?
Does it mean it's increasing?
Well, we have.
Height is increasing?
Okay, so yeah, because the v of 5 is positive, height is increasing. But I'm really getting at what does the value of v of 5 mean? What's the meaning behind that? So suppose it was 8 meters per second. what would that mean? 8 meters per second would mean what?
For any change in time, the resulting change in height is 5 times as large.
8 times as large.
8 times.
Jose, what were you saying about there?
That if the time change, for any change in time, change in height is 8 times
Right.
that change in time.
So we would just somehow say, for any change in time, that change in height is v of 5 times as much as that change in time. But I liked how Jessica said, what? Only for a very small time change, right? Why? Because it's only in the moment that we can consider this rate to be constant, because that rate is changing, constantly changing. So this is now true only for a moment right at 5. Because if your interval is too big, then you don't have constant rate of change. You don't have constant rate of change. Okay, so that's review and just orienting to the situation. So yeah, so dH is v of 5 dt. This is the key. This is how we make meaning of v of 5. That dH equals v of 5 dt. Okay, so you are going to you're gonna highlight points on the graph every 0.9 seconds. 0.9. Just do your best. This is for your sheet. And so we're going to define really big moments, right? So we just said that a moment in time would be small enough to have a constant rate. But now we're going to kind of loosen that restriction for a moment and say, okay, we're going to have really big moments. And we're going to, so up till now, many of you, okay, wait, don't start that because I'm talking. So, and I should continue. So up till now, lots of you are using the delta t and dt notation interchangeably. And so now we're going to distinguish between those two. So now delta t is going to be these moment widths, okay? These moment widths. So by highlighting points on the graph at every 0.9 seconds, we're saying our moment width is going to be 0.9 seconds. All right, and that's a big moment, right? We don't have constant rate in that size of a moment. Okay, but go ahead and do that. Answer this question in your table. Is that delta t, what do we think of that as a variable or parameter? We talked about variables and parameters, right? One day? I think we did. Remember that? So if you don't remember, talk about what the difference between those is, and then answer that question. No, just highlighting points. And then you're talking about this question. Is delta t a variable or a parameter, and why? And if you forgot, someone at your table remembers what we said about variables and parameters, and you need to share that. Some of you forgot.
Variable vary.
Okay, how'd we do? This table, did you guys discuss that? Tamisha, what did you guys come up with? Is delta t a variable or a parameter? Because?
No matter what, we want that to be 0.1, delta T 0.9.
And not change?
And not yet.
Yeah. So we have parameters can change, but they stay the same in a given situation. So if we could change the situation and now say delta t is 0.4, but now when we're looking at that situation, it stays fixed. So it's like what it is a situational constant. Okay. So in this situation, it's not going to, as we analyze this, it's not going to change. That makes it a parameter. Okay. All right. So now we're going to sketch the approximate rate function using the rate at the left side of each interval to define the constant rate for that interval. So we highlighted these points to highlight certain rates, which will be our constant rates for each interval. Use it, yeah. So for each interval, you're going to use the rate on the left side of the interval. And then I want you to have a discussion at your table. If we have the exact velocity, why are we doing this? If we have the exact velocity, why would we make a version of the velocity that's not as accurate? Why would we do that? So that's an important discussion. Talk at the table.
Yeah, so I guess we
More accurate representation of the distance.
Okay. If we have an exact rate of change function, why recreate it with an inaccurate version of that rate of change function? Why, Morgan? What you guys talk about?
Well, we talked about because there's an infinite amount of different rates of change
Okay.
in that line.
Right.
And so it would be impossible for us to use every single one of those to come up with like from that number.
Okay. So
So when we make these moments, these parts, we can estimate it decently well because we only have, in this case, 6 or 7 different rates of change. We can do that.
right. Good. So with constant rate of change, with these constant rates, we can actually make some progress towards finding height. Like you said, with a constant, continually changing rate, how can we figure out anything about changes in height or total height, right? But with constant rates, we can make some progress to start building up little changes in height and then total height. Okay. So, any questions? So now instead of using the real rate function, we're going to use this one. So notice that the point being highlighted is on our approximate rate function instead of the original rate function. So this is where we're going to move forward from, right? Using this approximate rate function. And we call that function r, right? So this velocity function, the real one in this scenario is v, and then just r by itself is this approximate rate function. Okay, so now we're going to freeze. So we imagine that time is going by and the rocket is speeding up, right? The rocket is speeding up. And then in our approximate version, what's it speeding up? It's going constant, but then it suddenly jumps. And then at a constant rate, and then suddenly jumps. So as a preliminary exercise here, we want to find the approximate height of the rocket at t equals 5. At t equals 5, using these moments of 0.9 seconds and a left side approach, the same way we built r. So what would it take? What would it look like to use that function r to approximate the height of the rocket at t equals 5? What would that process look like? So I've kind of frozen time at the moment t equals 5, and now we want to do some math and get an approximation for the height. In a broad sense, what would that look like, doing that? So how would you? So let's talk. So at your table, let's talk about that. What would the roadmap look like for doing that?
I was thinking, I mean, you'd have to start. Like, so it's yeah, and then you add that to this, which is two. Four sections, and then get to this one. 49 hours. We can use
Yeah.
Since the interval data set is 49, yeah.
Okay, so you're not doing it yet. We just want to get a roadmap. So don't start yet. So I just want to get the strategy, or like what's our vision for doing this. So Peter, what did you guys talk about?
To get to 5, well, you have to do the first interval and using your first rate from your first interval from 0 to 0.9 as your first rate, and then using that ending point as your new starting point, and then using the second rate from 0.9 to 0.1 or 1.8, and then just keep on doing the same.
Yeah, so I'm less about building the function with just getting this value of height at 5. So what would that consist of, just getting this height at 5? It sounded like you were more about, like you're talking kind of more about building the function, am I correct?
Yeah, kind of.
Yeah, so if we weren't just building the function, we just want to know what's the height of the rocket, or approximate height of the rocket at 5. What would you do?
If I had the graph, I would just...
What, Ben? What would you do?
I would just build the graph and just count and move it.
But we want to calculate a value. We want to calculate a value. So how are we going to find that value, Lauren?
You would have your initial y and then plus whatever change occurring in that moment.
Okay. So then what's the roadmap all the way to the end? So there's like something happening here, right? So we get the change for the first moment, right? Are we going to add up a bunch of moments? The changes in a bunch of moments? Not quite. There's a subtlety here that's not true.
You add them all together and divide by how many intervals?
No. So are you going to add up accumulated changes from a bunch of moments? Is what I'm asking. That'll give us the height at 5. No, why not?
Is that what accumulation means?
changes that much for a certain amount
Okay.
of time. So you have to multiply the time by how much it's changing and add those.
Yeah, so, yeah, right, yeah. We're adding up accumulated amounts of height.
Yes.
Are we adding up accumulated heights for a bunch of moments?
No.
Why not?
Doing it for each 0.9.
Because accumulated means that it's
Reach delta 9.
Okay, so you're not looking at the end. What's happening? There's something happening at the end, right? There's subtlety here at the end that you're not seeing. What's that?
It's only part of the law.
Right. It's not a bunch of there's a bunch of moments, but then there's only a part of a moment. This is important. You can't just add up all the changes from a bunch of moments. Why? Because at 5, you're not all the way through a moment yet. Okay, so we need all the changes in height from completed, what we call completed delta t intervals, and then what we call the current interval. The current interval is where x is at the current. So in which moment x is currently in. All right, so these are the completed intervals here, and then we have the current interval. The amount of change we're going to calculate for the current interval is not the change of a whole moment. Okay? So now do it. So you're not building the function. You're just approximating the height of the rocket at t equals 5. I give you the rate function. It's t to the 1.3. So now no estimating. You're not estimating any values from the graph. You're going to use that v of t was t of 1.3. So now we want to get an actual value that we're all going to get the same value, right? We're all going to get the same value for this estimate of the height at 5 seconds. Does it make sense?
Yeah.
Anybody have a question before you start? Okay, so we're all going to get the same number here. Get out GC, get out a calculator. We're going for a number here. We're all going to have the same number.
Because the first interval
Oh, Peter.
What's that? T to the 1.3. T to the 1.3.
Yeah, we're gonna add like the way I'm
Wait, 4.5 is Wait, but we can't.
So I got you focused on the numbers. I also want you to write out expressions symbolically that represent your calculations for 1 and for 2. So write out using all symbols, all symbols. So both get a number and write out these calculations symbolically with all this notation that we've got going around.
Okay, so I want us to say speed of.
Can we, do you still want the DT of the rate number?
What's that?
Do you still want like B of the specific times?
That would be your symbolic version.
Okay.
Yeah.
I didn't know if you meant like. All my rates
Yeah, so you will need the numbers for the times, but everything else you can do.
Do we still use 0.9 or do you want to use?
I tried to use it.
What do you mean? No, this. Can I put this or do I put this?
Yeah.
That's
I don't remember. I really don't, but you what are you doing?
I did it on PC, but I did was basic.
Yeah, looks right. Looks right.
Yeah, that's what I did. Okay.
Since they're all the
So
like
once the answers start coming in, let's compare. So what did you get? So just say it. Just say it.
17.82. 17.81.
17.81 for the total. Did Josh get something different? 14.281. Lauren, that's what Lauren got. Did you guys get that?
I got one.
Lauren, what did you get?
14.281.
14.281 something? That's what most people are getting.
Yes. So what about symbolics? I'm doing like,
Oh, it's because I put 4.5 in.
Did you figure it out, Oscar? Oscar, did you get your? Did you figure it out?
I wanted to check it out, see what that difference is. I don't know.
So I mean,
Just delta T.
Now I can add.
oh yeah.
Okay, now I got 14.
Yeah.
Okay.
14 point. Well, it just
What's up?
so we can use delta T for our known parameter. For this one, I mean, you can represent it numerically. Would it be
Yeah, I think
different
this is where we
parameter like delta T?
There's a name. There's a name for that. So that amount of change, right?
That's all jog my memory. Yeah, 14.28. There was a typo.
Okay.
My GC.
All right. So I think we're landing on 14.28. Okay. What about symbolically? So this first one, completed delta t intervals. Symbolically, what would that look like?
From 4.5
Available. Some people are punching. My hope is by the end of the semester that you would want GC and not a handheld. Because it is better.
It's so much smaller. It's so much smaller.
It is small, that's true. You got a laptop that's big. So in terms of putting expressions in, you can cut and paste, right? You can change it easily. It's much clearer to see. All right, Josh, what do you think for the symbolic way of writing this?
So I did 0.9 times the.
Can you symbolize that?
Oh, sorry, delta T
Delta T.
times the B of 0.9 plus B of 1.8 plus B of 2.7 plus B of 3.6, all multiplied by delta T.
Okay. So factoring it out's okay. You get the same number, but then we kind of lose what we're doing. So yes, that's perfectly fine when you're calculating the value, factor out the delta t. But as soon as you do that, then what happens? You end up in parentheses. You add a bunch of rates together, and that really doesn't have meaning. Does that make sense? So in terms of preserving the meaning of what we're doing, it's a little better not to factor it out. But in terms of calculating it, it's perfectly fine. Okay, so this first row would be a symbolic way of adding up all the change from the completed delta t intervals. And then the second one, of course, is the calculation itself. Okay, what about the current delta t interval? What about symbolically representing that? There you go.
dt, does it represent any change in t?
Okay, so dt is the accumulated height from the. So I still want to represent the accumulated height.
Then it'd be v of. Okay.
Go ahead.
You take the rate at the left, so v of 4.5.
V of 4.5.
And then times dt.
Right. So this is this amount. So the current interval. What we imagine x is increasing through the current intervals. It's like we've got these completed intervals, and those are kind of sitting there like a rock, right? But x is increasing, and it's increasing through the current interval. And so what? dt is a change within a moment, and it's a variable change. It's a change within a moment, and it's variable, right? So it varies from, what does dt vary between? What values? What and what? So dt varies between.
Between 0 and 0.9.
She wants dt to vary between 0 and 0.9.
Yes.
What would you be tempted to say that's not true?
4.5 and
4.5 and 5.4. That's what x is varying between, right? X varies between 4.5 and 5.4. But dt, the change, always varies from 0 to 0.9. Does it make sense? So now we're distinguishing between, right, what is delta t? It's our moment width. It's a parameter because we set up the situation and it doesn't change. dt then is what? It's this change in the current interval. As soon as you get to the next interval, it starts over at 0 and it goes up till 0.9 until the next interval. Questions on this slide? Okay, so maybe just to practice one more time, our task would be to, what time is it? We're going to do this in class or at home. But so to write the a function, and we've started doing that, right? So a function. And so what would be the overall form or structure of that, the a function? What would that be like? The overall form of that. Chloe.
What you would want to, kind of like something similar to what we did here. So you're talking about like for all intervals? Not just
Yeah, I want the whole function, right? I want this approximate accumulation function, which we'll call a. So what would just, in general, what would that look like, the structure of that?
You're going to multiply the rate of change for each interval times the length of the interval for how many intervals you have.
Okay. So just what's the so you're kind of getting more of the nuts and bolts of it. What's the overall structure of it?
Piecewise.
Yeah. It's gonna be a bunch of lines. So now what's the structure of each line? So we can say we're gonna need a line for each thing, and then what will the structure of each line be? How about Angela? Can you tell me? So that's what Chloe was kind of talking about. So each line would have what structure?
The rate of change.
Uh-huh.
X plus the sorry, I'm trying to find a way to fix it. Plus
So this is any line now, any line. So rate of change times And what would instead of AF, what would that number mean? So what would you be adding there? Just,
So it would be wherever it jumped from.
so what do we,
Initial, X, that's starting.
initial? So we're adding the initial X. Genevieve, tell me.
The initial height or the previous height.
The initial height or the previous height. So can you frame it in terms of completed and current interval? This is the accumulated height from what? From the previous completed interval. Intervals, all of them, right? This is the accumulated height from all previous accumulated. And what do we think about that? How's that look? Our rate of change times x plus the accumulated height from all the previous intervals. Agree with that? Brianna, you agree with that? Not quite. Not quite. Got something we gotta. Melanie, what do we gotta fix there? So rate of change.
The rate of change times X times change in, or just rate of change.
Yeah, so it's gonna be this is our dx. Now we want to write that in terms of x, right? So this is just what I'm writing out is just the meaning of that. It's not we're not actually writing out a good rule there. We're just writing out the structure of it, right? So it's going to be rate of change times dx, which gives, what does that give? Rate of change times dx? So it's the change in the current interval, right? The change in the current interval, because at the current constant rate times how much you've changed, plus all the accumulation from previous intervals. Okay? Which is what? This is our y initial plus the change in y. Y initial plus the change in y. So here's the deal. So this is a piecewise function. Every moment gets its own rule, right? Okay, our goal is to write this a function as a one-liner. As a one-liner. Okay? Not in a bunch of pieces. It's going to generate a bunch of pieces just like it's showing there. It'll be the exact same function, but we're going to do it in one line instead of piecewise, interval by interval. That's what we're going to start working on next. What's that?
In GC or like
Oh.
in
So no, yeah, we're going to work on it. We're going to work on it, the math of it, but then we're going to start using it in GC. And so in GC, it's going to be able to do great things for us, right? So this becomes problematic when what? When we have lots of intervals, right? So maybe we can set this up in GC for 5 intervals if we're really bored and have a lot of, endurance, 10 or 15. But what if there's 100 intervals? What if there's 200 intervals? And we want to graph this a function. We need it in one line. We need it not as a function of separate intervals, but in one line that gives us the whole thing. Question?
How is this different from the thing in the homework that you said had to be 10 different lines?
It's not.
You said
we
that.
just don't know it yet to be able to do it.
Yeah, no. So where we're going is instead of having to do 10 different lines, we're about to start working on how to do it in one line.
Right now we don't.
Right now we don't know, and so you're doing it as 10 separate lines.
Okay.
But so what we're going to embark on is how do we write a as a one-liner, as a one-line function, one rule for all. Okay. Does that make sense? Okay. Ready to start? Here we go. So just as practice, like one more time, maybe the written portion for Tuesday will be to write AX. It shouldn't take long. Okay. It shouldn't take long. You can do it. Okay. But that's your general form of it. It's going to be piecewise, and each piece is going to be a change in y. it's going to be accumulated y plus change in y. So that's what we're doing, A of t. Okay, so let's practice. Are all these meanings of things? I've got a nice object here. This one. Remember looking at this? We looked at this like the first week. Remember that? When we were talking about variables versus parameters. Now we can start making sense of this, right? We've got a lot to make sense of here. So where there's a single question mark, every place there's a single question mark, it is we're coming up with a notation that represents a value. It's notation that represents a value in the scenario. Where there's double question marks, it would be like a phrase or an idea. Okay? Phrase and an idea. So, or it could be notation, but doesn't represent a single value, right? So the single question marks, we want the notation. Those are all things that represent single values. We want the name or the notation for those things. Double question mark is going to be an idea or a phrase, not a single value. So your job at your table is then to identify what all these things are. Is the task clear? So let's do one together, an easy one. So this first one, we haven't defined this yet. So this right here is where we're going to start accumulating. And so we're going to call that x equals a. Okay, we're going to call that x equals a. So I'll show that. So lowercase a is what we're going to use to denote at what x value we're going to start accumulating, or start keeping track of an accumulation. So that's an example. So now so it's up to you to do the rest of these here. Work together. Got how many left? 6 left. Go. Yeah. Oh.
He gave us one for reading. That
Yeah.
Oh. Okay, so the first we have just parameters, which the one was the single. Yeah, definitely. We use full question mark. Yes, and then we'll use yeah, and then double question mark. You have like accumulated accumulation color. Sorry, the purple.
And then the yellow or the orange is
Yeah, because we talked about like how each line of A's would have the accumulation of the ingredients.
No, well,
Yeah, that's just a description. Since we started typing it, what do you mean the total? So if we're saying it's 9 times the black,
I think it's
okay.
You guys making progress?
Right, that's what I think. It doesn't have to be a type, like it's just a description. Yeah. So it's just a description.
I don't say the number.
Since
It's more about the value. The single purple question mark, it's about what is that value notationally. Don't worry that it's moving, okay? It could be this one, right? It could be this one. It could be this one, right? So it's just what is that value notationally? What's that representing? Okay, so now I gotta get a key for these questions. Because I never remember. I think the first one is I'm pretty sure the first one is the black question mark at the bottom. What do you think? So the black question mark representing, starting at the y-axis, out to the,
X.
What's X? How many people think it's X?
The one at the very bottom, right?
Oscar is confident, but the rest of you is kind of like, is it X?
Is it the very bottom?
Yes, it's X, right? This is X. X would be the value we represent it as the distance from the y-axis. So that's X. I think the next one is. Let's just do them all, and then I'll reveal them. Okay? I need to make a key for myself. I think the next one is the blue. Let's do the blue one next. What is the value of this distance? Dx. Okay, what about purple? Delta x. Good. Okay, and so then let's do the rest. I'll hold up on the red one for now. So what is the double question marks? Sing, what'd you say for the double purple question marks? What are those? It's not a value, this is just an idea. Yeah. Completed intervals. Okay, the double gold then. Bianca. Double gold interval is called what? Yeah, so talked about it earlier in class. Let's see. Jordan. Oh, what did you say? Current. Yeah, current interval. Okay, double red. Double red. What's the idea behind that? Kendall, did you guys get that one? Double red question marks? So what kind of function? Okay, and what kind of rate of change is it implied? Double red. So that's referring to the red curve. Yeah, changing rate of change, exact rate of change, right? Exact rate, and then the double black. Sam, what's the double black? Double black is exact rate of change? Approximate rate of change, right? Okay, so let's reveal them here. Dx, yes. The next one. Come on. Delta x. Next one. Completed intervals. Current interval. Okay, so when we have the subscript r sub f, that's like the exact rate function for some accumulation function f. Okay, so the accumulation function f, this is the rate of change of f. And then the black double, what's the notation we use for the approximate? just plain r, right? Just plain r was the notation we used for the approximate function. Okay, so how about this last question mark? So how can we describe what that's doing? How will we describe the red question mark? Yeah.
The left endpoint of each delta T.
Okay. Of each. So.
Current. Yeah.
Right. It's the leftmost x value of the current interval. It's the leftmost x value of the current interval. Or the starting value of the current interval, you could say too. Yeah, the starting value of the current interval.
But I mean, we've got two different red dots. We've got one that represents like the starting x value and then the starting value like on top on the function.
But a point on a curve is not a value, right? What is a point on a curve? Yeah, right, pair values. So it would be the x coordinate of that point would be this left end of the current interval. Right, and then the y value of that would be?
Yes, sir. Which is also the argument.
Would be what?
Which is also the argument.
Yeah, so right, exactly. Okay, cool. So the next thing we're going to do, you're not going to make this, but you're going to make something similar to this. So, because this is very intensive in terms of getting the bars to look right and the fonts to look right, and that. So, we'll do something that has all the same mathematics as this, but won't have all the burden of the prettiness of it. Okay. But now that being said, the prettiness is important in terms of a didactic object, right? So it's got to be really clear to the students what things mean, and so I spent a lot of time on the aesthetics of this, so that it was the most effective as it could be as a didactic object. Okay, so that is important, but we want to focus on the mathematics for now. Okay. All right. So now we're ready to start talking about this. Can we make this function in one line? This accumulation function in one line? Okay, so this has to do with this kind of idea that you know how fast the quantity's value is changing at every moment. What's that? That you know how fast the quantity's value is changing at every moment. What's that? That's the rate of change function, right? We want to know how much of it we have at every moment. What's that? Accumulation, okay? So we want to do that not as a big, ugly piecewise thing there's lots and lots of intervals, but with one rule. Okay. So here's a snapshot of what we just looked at. So how much do we have at x equals, how much has accumulated starting at A up to x equals 6.75 based on the approximate rate function r? So we've kind of asked this question before, what would that look like? Computing how much accumulation we have starting at A up to 6.75, what would the general roadmap of that be? General structure roadmap of that be? What would we need to do to get that amount of accumulation starting at A, ending at 6.75? We don't know what R of F is. So we don't know what F is, and so F is some accumulation function. We don't know what the quantity is, and then R is its rate. So now we're just being general here.
So the sum of all the accumulation of the completed intervals plus the accumulation of the current intervals.
Very good. Very good. All right. So there's that, right? So it's going to be, we're going to sum up the first three terms there is what? Change from completed intervals, and there's 3 of them, plus a little more change from the current interval. Okay? Oops. So now the question is, what are these input values into the R function? Right? So to get, so what is, so you guys talk about the tables. What's that going to be? What are we going to input into R to get the right rate for the second interval, third interval, and the current interval? Go. So what will those be? Hopefully you didn't see.
But it's one R.
Because the DS or A plus
Okay, let's see. So what'd you guys have? Alex, what'd you guys talk about so to get the rate for the first interval, how will we get that rate? What's that? R of 2? Okay. No, so that's A is not necessarily at 2. But that's the key to it. That it's the A, which is not necessarily at 2. So it'd be R of A, right? And then to get the rate for the second interval, so this would be this x value right here. A plus delta x would be that. So it would be A plus delta x. And then third interval, and then the current interval. Is this what you guys said?
It's not just determined. So the rate happens at A plus 3 delta x, and then dx is the interval time.
Oh.
So it's always like
Yes, it's on the outside.
it's always like.
Okay, so notice that what we're adding up is really the same thing every time. What is it? It's m times change in x, right? These are all little dy's, all 4 of those. So yes, the last one's the current interval. It's shorter, but it's the same thing. It's m times change in x plus m times change in x plus m times change in x plus m. We're accumulating changes in y, right? So we can write these complete intervals using summation notation. No, this is good because you don't have to do all that writing. No, listen, you guys. Oh yeah. Okay. See, this is good because now you don't have to rewrite the same thing over and over and over again. That's all that means. It just means sum up a bunch of things that all look alike, right? There's just a subtle difference between each one. What's the subtle difference between each one?
Coefficient.
Not coefficient, but coefficient is a multiplier outside, right? So what is slightly different about each one? The x value where you're going to get the rate from, right? That we're inputting into R.
I was thinking coefficient next to delta x.
Right. So it's a different rate, but what's different about each rate is just what's going to be different in the formula is just what we put in, okay? So we want to figure out then we need a formula for what goes inside R so that for any given j, so j is the interval number, okay? So the first interval is going to give us that little amount of change, R of A times delta x. Second interval and third interval. That's what j means, which interval we're in. So what is the formula? Given interval, say 3, what do? We have A plus 2 delta x. give an interval to a plus a single delta x. Why? Because we're only going to the left side of it. So the number of intervals that we jump to get to the second interval is one interval. The number of intervals that we go through to get to the third interval is 2. So who's got the formula? Brianna.
A plus J minus 1.
She wants a plus j minus 1 delta x. Oh, you're also smart. Right. So you're going to go a plus j minus 1 delta x's to get to the left side of the current interval.
Why can't we just start J at 0?
Because we want j to be the interval number. So we want, think about the first interval, j equals 1. Second interval, j equals 2. That's helpful. Okay, so look. So now we can x is increasing, we're increasing through the intervals, and now we've got the total accumulation from what? What is that? The total accumulation from? For what part of this? Completed intervals, right? And so now we could have 100 completed intervals, and it will still, all we'd have is 100 instead of a 3. And now it'd be summing up for 100 completed intervals. So for now, the next thing we need to do is figure out what's the change in the current interval, and that depends on x, right? That depends on how far in the current interval where we are. But we've got the sum total of the change for the completed intervals. Again, all that's saying is sum up m times change in x plus m times change in x, just summing up dy's, summing up dy's. Okay. So you're finishing the GC project that I assigned Tuesday, part 2 of the oil slick, and then you're writing the A function for the rocket basketball, the long way, right?
Oh, not
She's skipping the day. She's catering for a wedding.
You guys good? You good?